In this video, we are going to solve two examples for how to perform a test for independence and also how to perform a test for homogeneity of proportions. Now, in the past, we discussed the association between two variables by examining the conditional distribution in a contingency table. The data presented in the contingency table represent the measurements of two categorical variables on each individual in the study and allow us to describe the association between the two variables. And now we introduce an inferential method to determine whether an apparent association between the two categorical variables is statistically significant or not. So if you have a single population in which the two variables are measured on each individual to assess whether one variable might be associated with another, we conduct a test of independence. And if you have two or more populations, again, for one single population in which the two variables are measured on each individual to assess whether one variable might be associated with another, we construct a test of independence. But if you have two or more populations in which you want to determine equality of proportions, to determine if they are equal or not among the populations, we conduct a test of homogeneity of proportion. Let's take a quick look at the examples. Are health and happiness related? This is the question. The following data represent the level of happiness and the level of health for a random sample of individuals from the General Social Survey. So the happiness, we have three categories: very happy, pretty happy, and not too happy. And for the health, we have four different categories: excellent, good, fair, and poor. Thus, the evidence suggests that health and happiness are related and use the 0.05 level of significance. So in this case, to determine whether there is a statistically significant association between the two categorical variables, we perform a chi-square test of independence because we have a single population in which the two variables are measured on each individual to assess whether one variable might be associated with another. The chi-square test for independence is used to determine whether there is an association between a row variable, so we have the rows here for the happiness, and the column variables, which is the health. We have four different ones in a contingency table constructed from the sample data, which is this one right here. Now, the null hypothesis is that the variables are not associated or independent. So that is the assumption for the null hypothesis, is that the variables are not associated. So two of them, the row and the health, they are independent. That is the null hypothesis. And the alternative hypothesis is that the variables are associated or they are dependent. So the first thing is we need to figure out what is the expected counts for this table. So that is the very first steps that we need to find. And before we can do that, we need to compute the row and the column total. The row and the column total. So let's do that. So I can find the total. I can find a total for each of the row. So I take 271, add to 261, add to 82, add to 20, and I get a total of 634. And then I add again the row these four numbers together, and then I get 1098. And then if I add the four numbers of the last rows together, I should get 264. If I add 33, 103, 92, and 36. So that is the total of each row. And now I need to find the total for each of the column as well. Okay, so total. So I need to add three numbers here together. I get 551. These three, I get 931. These three, I get 405. And then these three, I get 109. Alright, so after we get the row and the column total, this is the total for each row, this is the total for each column. Now if I add these three together, if I add these three together, everything together, or everything together here, I get the total of everything is 1996. So if you add all the number of the rows or the columns, the total rows or the total column, you should end up with a single value. The total of the table is 1996 together. Okay, so after we get that, we can find the expected counts. So we can find that. Let's do it here. Expected count. We are looking at the expected count, and that is calculated at what? The row total multiplied by the column total, and then divide by the table total. So the row total, the column total, and the table total. So we can use this formula, the expected counts, and then we can find that for each of the cells inside the table here. So for example, let's consider the first one, 271. Now if I look at this cell, the single cell right here, I want to find what is the expected count for this specific location. Well, I take the row total. Let's do the expected count for the 271. So I use this one as one example and apply this formula here to find the expected count for this single cell. So the row total for this cells, we see that the row total is 634. So 634 for this cells. And then the column total for this cell, you go in the vertical columns, you get 551. And then the table total is the red number, the total of everything, 9996. And if I do that, I should be able to get the approximation 175.017. And that is the expected count. And let me put it right here. So this is only for one cell only. And then we use the same formula. You do the same thing for this cell. So the next one right here, the row total, the row of this row is still 634. But then the column total is number 931 right here. And then still dividing by the table total, which is 1996, which is everything. So you just follow the same formula for each individual cells, each individual number here. And then you should get the following value here. So the next one, you should get 295.718. And if you do the same thing, you should get the expected count at 128.642. And then this one, you should get 34.622. and the rest of the values are here. Okay, so after we find the expected counts for all the cells, the next step is we can find the expected, make sure that all the expected frequencies are greater than 5, so the requirements for the chi-square test are satisfied. So make sure that all the expected frequencies are bigger than 5. And yes, all the expected frequencies we just found, they are all bigger than 5. So we can go ahead and use the chi-square test for the next steps. So the next step is we need to find the test statistic for the test of independence. So that is the next steps. So the test statistics is given as chi-square is equal to the sum. This is the test statistics. The summations OI minus EI square divided by EI. The EI right here, this is the expected numbers of the counts in the I cells. So the blue color right here, the number that we found using this formula is the E, the expected counts, and then the one that was given for you from the table, the black number, the data, those are the observed value. So the black one is the OI, the observed value. The blue one is this EI, the expected value. So you can just take this number minus this number and then take the square and then divide by the expected number and then just keep adding. The summation means you just keep adding for all of the value on the table, right? So we can do that. So let's do the first one. The first one, I take 271. I subtract the observed, subtract the expected value of frequency, and then I square that value and I divide by the expected EI, which is 175, the second number. And then this is the summation, so I keep adding. The next one, I take 261 minus 295, 718, square, divide by the second number because that is the expected frequency. And then I just keep adding the next one for each of the cells. So I just keep adding and repeat all the process until I get to the last cells. And the last one is what? 36 minus 14.417, the whole thing square divided by EI, which is the second number. And if you do all the correct calculation for everything, you should be able to get the approximation of 182.173. And this is the test statistic. And after we get the test statistic, the next step is we need to find the degree of freedom. We need to find what is the degree of freedom. Okay. So the next thing is we need to find degree of freedom. Or DF, the DF value. So the DF value, how do we calculate the DF value? Well, the degree of freedom DF has the formula of R minus 1 and multiplied by C minus 1. R is the number of the rows, C is the number of the columns. How many rows do we have here? We have 1, 2, 3. We have 3 rows. So I have 3 minus 1. how many columns do we have? I have 1, 2, 3, 4 columns. So 4 minus 1. 3 minus 1 give me 2, and 2 times 3, that is going to be 6. So I have 6 for the degree of freedom. Okay. So at this point, I think it is good that we recall what is the null hypothesis again and what is the alternative hypothesis, H0 and H1. So again, as I mentioned in the beginning, the null hypothesis is that the variables are not associated or they are independent, and the alternative hypothesis is that the variables, they are dependent. In this case, we are having two variables, the happiness and health. So the null hypothesis say that they are independent. So you can say that health and happiness are independent. So we assume this to be true. Health and happiness. This is the two variables in the problem. So health and happiness are independent. And for the alternative hypothesis, we assume that we say that, okay, they are not independent. Health and happiness are not independent. That means they are dependent, right? Not independent means dependent. So this is the null hypothesis and the alternative hypothesis. Well, there's a few ways that you can get to the conclusions. You can use the classical approach by using the critical value, or you can apply the p-value approach. Okay, let's just go with the classical approach first. Classical approach, or the critical values methods. Alright, so we know that this is the chi-square. The chi-square is not symmetric, right? So this is the chi-square distributions. And this one is the critical region, right? This is critical region, which is the area has the value of alpha. And alpha is the significant level. In this case, we have 0.05. So the alpha, the area here is 0.05. And we need to find what is the critical value. What is the critical value of the chi-square of alpha? And compare. We are going to compare the value of the test statistic and the critical value. So first thing is I need to find what is this value. Well, alpha is 0.05. So you are looking for the right area of the chi-square of 0.05 has the area of 0.05 with the degree of freedom is 6. So you can use any of the table, any of the chi-square distribution table, and because the degree of freedom is number 6, so I look at this row and I know that the area to the right of that critical value is 0.05. So I go ahead and find 0.05 with the degree of freedom is 6, and that gives me this value here. So 12.592. 12.592. And because what? Our test statistics is 182.173, and that is way beyond the number 12, right? So it's somewhere here. This is the the test statistic 182.174, something like that, right? So 182 is beyond 12 point something, so of course it's gonna be on the to the right, and it will be inside the critical regions. Now, if that is inside the rejection regions, we reject the null hypothesis, because the test statistics is inside the rejection region here, and therefore we reject the null hypothesis. So because this one is bigger than alpha chi-square, the critical value, which is inside the critical regions, therefore we reject the null hypothesis. We reject the null hypothesis. So that is the classical approach. You can also use the p-value approach. So let's try that. P-value approach. And for the p-value, you can also draw the curve. Oops. The chi-square distributions. Again, this is not symmetric, okay? Something like that. And then right here, this is your test statistics. The value of your test statistic, which is 182.174. And we are looking for the area right here. This area is the p-value. So this is the chi-square. We can apply the functions from the TI-84 or 83. I think the TI-84 has a function for the chi-square, but I don't think the TI-83 has it. So make sure you use the newer version of the TI-84. You should be able to get this function. So you go second vars to get you to the distributions. And this is the chi-square, so you pick the option of chi-square CDF. It will give you the area, the cumulative area, and the lower bound we stack from right here, which is 182.174, and you want to find the area from this point to all the way to the right. And the upper bound is all the way to the right, so I go all the way to the right as long as I pick a very large positive number. So 9999 all the way to the right. And I know that my degree of freedom is still the same thing, right? The value is right here, 6. So I got that. And you put 6 in and just paste the value and then hit the enter. And this is what? This is 1.171 to the 10 to the negative 36. So let me do that. Chi-square CDF. We go from 182.174 and we go all the way to 99999, and then the degree of freedom. This is the command that we are using, and you get the answer of 1.171. 1.17. Oops. 1.171, and this is 10 to the negative 36. So this is an extremely small number, and you can think this one is like 0, right? Because this is almost 0, a lot of 0 to the power of negative 36. So the p-value is like 0, and of course the p-value is 0, and that is less than alpha, which is 0.05. So anytime the p-value is less than alpha, we reject the null hypothesis. We reject the null hypothesis. And that is the same conclusion that we got up here. So either way, if you use a classical approach or you use a p-value approach, you do end up with the same conclusions if you do it correctly. And because we reject the null hypothesis, that means we have enough or sufficient evidence to say that, okay, the health and the happiness are not independent, or they are dependent. So there is sufficient evidence at the level alpha equals 0.05 level of significance to conclude that health and happiness are related. And this is the conclusions for our problem. Now you only need to solve one approach here, either the classical or the p-value. You don't have to solve both ways. As long as you solve either this one or this one, then make the rejection or not, and then make the conclusions. All right, so we went over a long process for how to conduct the test for independence by hand with a lot of calculations. And if you make a very simple mistakes for the degree of freedom, the rows, or a single number inside the cells, then you will mess up everything, and we might not be able to get to the correct conclusions. So it is also a good way that you can also check with the graphing like TI-84 calculator to make sure that for this type of calculation we do end up with the same numbers at the end. So let's try to use the TI-84 calculator to carry out this test of independence for this table from the beginning. Alright, so I will show you here. So first thing is you need to enter the value of the table. This is the table with 3 rows and 4 columns. So you need to enter the value, the data from the beginning, the black numbers, without any calculation first, right? So let's go to the matrix. So you want to use the matrix to enter the matrix with 3 rows and 4 columns. So to access matrix, I use the second button, and to hit this button here so that I get to matrix. And then I move the cursor to edit, and I choose the option 1, matrix A. I know this matrix has 3 rows and 4 columns. So I put 3 and then 4 and hit enter. And now I need to enter the data, the observed value 271, and then the next one is 261, and then 82, the first row, and then 20, and then enter 247, 557, 567, 231, and 53, and then I hit enter, and then the last row 33, 103, 92, and then 36. And after you get that, you are going to hit second and hit this one so that you can quit out. And now you go to start, and then we go move the cursor to the test, and then scroll down and find the chi-square test, because we are looking at the chi-square test for the independent. So you hit enter. Now the observe is the matrix A, the matrix that you just enter, right? You enter into the matrix A, and then we put the expected as the matrix B. So just put that as matrix B. It's the default value. So A, B. Okay, and then you go to calculate, and then hit the enter. Hit the enter, and it's magic, right? It gives you the test statistics, which is 182.173, and it gives you the degree of freedom is number 6 we got here, and it also gives you the p-value 1.171, 10 to the negative 36. So everything is matching to our hand calculations. We went over the whole things like half an hour to carry out all of these calculations. And now with just a few simple clicks and using the chi-square test, you have everything. The p-value is what we need at the end so that you can make the conclusions. Whether the p-value is less than alpha or bigger than alpha. Less than alpha, we reject the null hypothesis. Bigger than alpha, we fail to reject. And in this case, we can make the conclusion very quick if you know how to apply the TI-84 to confirm the answer. So we just saw an example of how to conduct a test of independence, and now it is time to see one example of how to conduct a test of homogeneity of proportions. This is just an extension of the two-sample z-test that we introduced earlier. And in the chi-square test for homogeneity of proportions, we test whether the different populations have the same proportion of individuals with some characteristics. If you have two or more populations in which you want to determine equality of proportions among the populations, make sure that we conduct a test of homogeneity of proportions. And the procedures for performing a test of homogeneity are identical to those for a test of independence. But now for the null hypothesis, we simply say that the first proportion is equal to the second proportion and equal to the third proportion, and we make that assumption to be true. And then for the alternative hypothesis, we say that at least one of the population's proportion is different from the others. Alright, let's take a quick look at the example. So in a recent survey conducted by the Pew Research Center, a random sample of the adults of 18 years of age or older living in the US was asked their reaction to the word socialism. So in addition, the individuals were asked to disclose which political party they most associated with. The results of the survey are given in the table. So we have Democrat, Independent, and Republican parties. And there are two values here for positive and negative. So this is the number of the people say that they have a positive for Democrat and Independents and Republican and so on. So explain why this data should be analyzed by homogeneity of proportions instead of the other one that we just saw, which is the test for independence. Well, because we have three distinct populations that are being surveyed: Democrats, Republicans, and Independents, and the response variables is qualitative with two outcomes, positive or negative. So we analyze the data using the homogeneity of proportions. Remember, we have three distinct populations. So go back to the beginning of this notes here. If you have two or more populations, okay, two or more populations. For the test of independence, we only focus on a single population. But this one, two or more, then we conduct a test of homogeneity of proportion. And that is the case here. We have three distinct populations that are being surveyed: Democrats, Independents, and Republicans. And while the procedures for the test of independent that we saw earlier and the test of the homogeneity proportion, they are the same, the data differ. And how? Now, in the test of the independent that we saw earlier, we are measuring two variables such as the marital status and the level of happiness on each individual. Now, in other words, a single population is segmented based on the value of the two variables. But for the test of homogeneity of proportions, like this case, we consider whether the proportion of the individuals among the different populations have the same value or not. So that is two or more different populations. but for the independent test, we focus on one single population. So if you have a single population in which the two variables are measured on each individual to access whether one variable might be associated with another, make sure you use the test of independent and not this one. Alright, let's go to part B. Does the evidence suggest individuals within each political party react differently to the word socialism and use the 0.05 level of significance? So again, similarly to what we did for the test of independence, we need to find the expected counts for each cells. So I can do that here. So we have this table, okay? So contingency table. Now we perform the total calculation, the total, and also the total for the column as well right here. Okay, so if I add 220 and 278, if I add them together, I get 499. And if I add these two, I get 554. If I add these two, I get 413. And then if I add all the rows, these rows together, I get 426. If I add these three, I get 1040. And make sure if I add these two, I get 1466. And if I add these three, I still get 1466. So this is the table total. Okay, the table total. We call this value is the table total because this is the sum for the vertical and horizontal values. So now for each cell inside each cell, we need to figure out what is the expected count. So let me just pick one example right here for 20. So I'm going to pick 220. So go down here. For this cell, I want to find the expected count. Expected counts. And I can do this using the formula for the row total multiplied by column total divided by the table total. Okay, so for 220, the row total, so we go all the way with this row to the right, that is 426. And then the column of this cell is right here, the column total is 499. And then the table total is always this number, 1466. And if you do that, you should get the value of around 145.003. 145.003. And then I just keep doing the same thing for this cell, this cell, this cell, this cell, this cell. Then using the same formula here, then the expected counts are, for this one I should get 160.985. And this one I should get 120.012. This one I should get 353.997. And this one I should get 393.015. And this one I should get 292.988. So after I get all the expected counts, I'm going to check to make sure that all the expected frequencies are bigger than 5. So all the requirements for a chi-square test are satisfied. This is bigger than 5. This is also bigger than 5. Make sure all the expected frequency, they are all bigger than 5. And if that is the case, we are okay to move on. Okay, so make sure that we check all expected frequency bigger than 5. So chi-square test is satisfied. Okay, so the next thing is I need to find the test statistic. So chi-square, this is the summations of the observed value minus the expected value square divided by the expected value. So I look for each cell. The first cell, let's do the first one. The black numbers, those are the data, the observed value. Okay, so for the first one, OI is the observed. I have 220, and the expected value is the one we found using the formula 145.003. And then square that, and then the same number I rewrite down here. And this is the summation, so I just keep adding all of the cells together. I do the same thing for this guy, this guy, this guy, this guy, and the last one. The last one, the observed value is 351. OI is 351 minus the expected value 292.988, 292.988 square, the whole thing. And then divide by 292.88. And that would give me 96.733. And the degree of freedom is my next value that I need to find. The degree of freedom, I know that I need to take the number of the rows minus 1. In this table, I have 1, 2 rows, right? Positive and negative outcome. So 2 minus 1. And I multiply with the number of the columns. I have Democrat, Independent, and Republican. So 3 of them. So 3 minus 1. So I should have 2 times 1 is 2. So the degree of freedom is 2 in this case. Now we need to set up the null hypothesis and the alternative hypothesis. So the null hypothesis is the assumption that all the 3 proportions, they are equal. So we say that the proportion for Democrat equal to the proportion for Independent Party equal to the proportion for Republican Party. And we say that for the other alternative hypothesis, we say that at least one of the proportions differ. So at least one of them is not equal to the other one. So this is the hypothesis setup. Alright, so how do I check? Does the evidence suggest the individuals within each political party react differently to the word socialism? That means we need to check if they have the same proportion or they don't, right? So we need to check if we reject the null hypothesis or we fail to reject. Well, we can use the chi-square. We can use the p-value approach for this one. Now we have the alpha level is 0.05. Okay, so alpha level is 0.05. Therefore, you are looking at the p-value. So to test with the alpha to see if the p-value is bigger than alpha or less than alpha. So let's try to use a TI-84 for that. Okay. You know what, actually, let's just use the classical methods first, and then I'll do the p-value methods, and then we will compare them. Alright, so we will use the classical approach, which is the critical value methods. So this is the chi-square things, right? This is chi-square. And right here is the chi-square of alpha, right, which is 0.05. So this is the area to the right, 0.05, and this is the rejection region. Now I need to find out what is this value right here. So we know that the value, the area below this value is 1 minus 0.05, because together everything is 1. So I'm going to use the chi-square table to help me to find that critical value. So I know that right here I have the area to the right of this critical value is 0.05. So we go back to here, 0.05, the area to the right, 0.05, this guy right here, and we know that we have 2 degrees of freedom. So you would go to find 2 degrees of freedom, and it gives you 5.991. So this value right here is 5.991, and your test statistics is 96, right? 0.733. Your test statistics, this is 5.991, and 96 is like all the way here, right? This is like the chi-square, like 96.733. So 96 is way after 5.733, and this is the test statistic. And because this area right here is the rejection region, and because the test statistic is inside the rejection region, therefore we reject the null hypothesis. Reject the null hypothesis because the test statistic is bigger than the critical value. It's inside the rejection region, so we rejected the test statistic. I mean the H0. So that is the classical approach, and you can also use the p-value approach, and we can draw the same way. My test statistic is right here, 96.733. And I'm looking for the p-value. This is the p-value, and we can use the chi-square CDF functions on the TI-84. So you want to look for this area. So the lower bound is 96.733, and you want the right bound, the right limit all the way to the right, so 999, and the degree freedom that was 2. So let's see, what do I get here? So if you go to second var, get you to the distribution. If you scroll down, chi-square CDF that gives you the area with the lower bound, 96.733. the upper bound is 9999, degree of freedom is 2, and then you just paste this into the formula and you get the value of like 9.87 10 to the negative 22. Wow, this is extremely small with a lot of zero, right? So that is like 0 because it's extremely small. So you can think of that as 0. And of course 0 is less than alpha. Alpha is the 0.05. If the p-value is less than alpha, we also reject the null hypothesis. So either way, you still end up with the same conclusions. We reject the null hypothesis. Okay, so if we reject the null hypothesis, that means this one right here, I just reject that. That means I have enough or sufficient evidence to say that at least one of the populations differ. Or you can make the conclusion that a different proportion of the individual within each political party react positively to the word socialism. So that is the conclusions. So there's sufficient evidence that the alpha level of 0.05 level of significance to conclude that a different population of individuals within each political party react positively to the word socialism. And that is how we conduct the test of the homogeneities of proportions. The process is similar to the test of independence, except that when we talk about the null hypothesis, we say that okay, the three proportions they are equal, and the alternative hypothesis is that at least one of them will be different from the other one. And then the other ones, for the test of independence, the null hypothesis, we say that okay, the two variables are independent, and the alternative hypothesis is when they are not independent. But the process of conducting the test is the same thing. And also, we can also use the TI-84 to conduct the test just the same way as we did before. Let's try that again. So first thing, you need to access the matrix, so second matrix right here, and then we pick the first one, matrix A. No, sorry, you have to go to edit, go to stat, no, go back to matrix, second matrix, but go to the edit because we need to edit the matrix first before we use that. Alright, so click on that, and I know that this matrix is this table. So we have two row, okay, and we have 3 columns, right? So 2 by 3. So you go ahead and we enter all the entries for the observed matrix. So you want to enter all the data given for you in the beginning. So 220, 144, 62, 279, 410, and 351. And then now we just quit, second quit, and then now we press start. All right, and then we go to the test, and then we pick the chi-square test because we're using the chi-square test. So chi-square test right here. The observed matrix is the matrix A we just input. Okay, and with the cursor, we move to the expected matrix and make sure that you put the matrix B in, and it will automatically calculate that for you. And then all you do now, we just go to calculate and then hit the enter. and you got everything here. Let's check the answer again. We got the test statistic 96.733. The p-value, let's give you only the p-value. The degree freedom is 2, which is correct, and then p-value is 9.87 10 to the negative 22. So the chi-square test only give you the p-value and the test statistic, and you can make the conclusion right away after we run the chi-square test. So that is how you use the TI-84 to perform the test of independent and also the test for the homogeneity of proportions.